All right, how's it going, everybody? We are here on Thursday, February 25th, and today we're going to talk about approximate integration. This is section 7.7. This is a pretty cool day. This is going to be quite a bit of a distinct day from things that we've been doing over the last couple sections here. Um, the difficulty associated with this section is different than the difficulty that's been associated with the first five sections of this class. In that this section involved, and by the way, you're going to see an absolute ton of writing here today. That doesn't mean that the math is hard. That means that there's lots of things that we need to explain. So today is going to be kind of a heavy day on the reading and the writing, but at the end of the day, all we're going to be doing is a whole bunch of geometry today, right? And although that's in a sense, that's all we've been doing all semester, right? So this section involves a significant amount of simple computations. And what I'm going to suggest to you is that you would benefit from finding ways to perform these computations either in your TI calculator, in Excel, or using Python, right? A little programming language here. And that's what I'm going to do today. So you're going to see me write a lot of Python code today, and that's because I have very, very little interest in doing mountains of multiplication and addition by hand because that's not interesting to me. And so what I am going to suggest to you guys, and this is not required, but I think this is a pretty good idea, is for you guys to also write some Python code and imitate the things that I'm doing here. The reason for doing this is because we don't want to do any of this computation by hand. We're going to do so much addition and multiplication today that I want to have a computer do it for me in a really concise and simple way. After I get through kind of my introduction here, I'm going to show you guys where you can download and install the same Python setup that I'm using right here. It's an easy one download, one installation, and you've got everything that you'll need. And then you can imitate the code that I'm writing to basically have everything done for you this section here. There's two really big reasons why we care about this section, right? Approximate integration. Why do we care to approximate the value of integrals? Well, one, something that we've been talking about is kind of a big theme of section 7.5 is that most functions aren't integrable. Most functions don't have antiderivatives. And so there's no way for you to actually perform the computation that you're interested in performing. That's really limiting for us. If we want to know the area underneath sort of any curve, we need to be able to approximate it geometrically really well, even though we can't technically do the calculus step of finding an antiderivative. The other thing here is that even if all functions were integrable, it's still not actually a big help to us. In most settings where you're applying the concept of an integral, you're going to be working with data that's been collected in a table rather than a function, right? Where there's not really a function that's available to represent the data, but you've got a bunch of points in space. So we don't have a function that we can integrate over, even if all functions were integrable. So for example, if your car records velocity once every 20 seconds, then all you've got is a bunch of velocities at 20-second time intervals. Even though we probably can't come up with a formula that would suggest that would fit through all of those velocity points that would be useful to us, we still should be able to estimate the total distance that's been traveled, even though we don't have a formula, right? Even though we're not directly performing integration. So that would be an excellent example of a place where we might want to use one of our approximate integration techniques because the area underneath the velocity curve is going to be distance. Even though we don't have actually a curve, we just have data points, right? And again, at the end of the day, none of these approximations should ever really be done by hand, except for like in a class like this, we're going to say, okay, use 4 subdivisions to approximate this. That's never really going to be actually a good approximation. That's just something for us to do by hand to get a feel for what these formulas do. If we're ever going to want to get a good approximation, we're using technology, period, right? Nobody really makes good integral approximations all by hand. So we want to understand these techniques because they're exactly the same approximation techniques used by technology to estimate areas. So every area estimate that you're ever seeing is some form of probably one of the 5 rules that we're going to look at today. And a good thing also for us to realize as we get into this today is that, and I'll say here, now that you are reaching mathematical adulthood, right, getting beyond Calc 1 is a big step right here. You should realize that there's not really any value in forming an estimate if you don't know how good the estimate was. All right. So one of the other things that should always go along with every single thing you ever learn about making an approximation for the entire rest of your life is an additional discussion of, well, how good do we think that approximation is? Do we have a known amount of error that we're possibly accruing with this estimation here? Do we know how many subdivisions we want to break our Riemann sums up into if we have this maximum allowable amount of error? So discussing the error associated with approximations, those things should always go hand in hand. We never want to approximate things and just say, that's my guess. Well, how good is the guess? We want to know. The good news is that understanding all these techniques is for the most part pretty easy. We're already familiar with several of them. So today what we're going to do is we're going to look at these 5 approximation rules right here: left hand, right hand, midpoint, trapezoid, Simpson's rule. And we're also going to look at some error analysis that's associated with these guys as well. I will say that the first 4 are strictly geometry problems. The 5th one, Simpson's rule, is going to actually require a little bit of calculus for us to derive its formula. The first 4 are things that are it's nothing more. I could teach a 9-year-old the first 4 rules. Might take me a little while, but a 9-year-old could do all the math. Number 5, Simpson's rule, a little bit tougher than the rest out there. All right. So what we're gonna do is we're gonna cruise through the 4 easy ones. And by the way, like, you've already seen these, right? I expect everybody's seen left and right hand rule. I think that most all of us have seen the midpoint rule. I bet that most of you skipped over the trapezoid rule in Calc 1, and that's not really a big deal. It's not going to blow your mind. It's just a slightly different way for us to do our geometry. And I don't think that any of us saw Simpson's rule in any time in the past here, so I'm assuming that this is new to all of us today. So again, before I get into this right here, I want to kind of show you where you can get your own Python setup, because I am going to spend about half of today writing some Python code to do our approximations for us here. That's going to be important, right? So let me pop over real quick to my browser over here. And what I want to show you is where you can go to use the same setup that I'm using here. And so in my new tab here, I'm going to do a search for, I'm going to do Python Anaconda, download, right? Whatever. And that's going to take me, we can see right here our installation. You can see it's purple because I show this to people all the time here. And clicking on this guy here, it's going to take me to wait a minute, is this the installation page I'm looking for right here? Wow. Why is this different than the one that I feel like I normally see here? Anaconda Individual Edition. Maybe this, does this page really change here? Holy cow, did they like change the way that all of this looks right here? Is this seriously not? Installation. Okay, well, installing on Windows. Download the Anaconda installer right here. I'm looking at it right here. So I'm gonna, okay, here's what I was looking for. Anaconda.com/product/individual. And this is really the page that I was recognizing that I was looking for right here, this download button. So the important thing that this comes with is a variety of things, right? And I feel like they had like a list right here. So the important thing is that we want the programming language Python. We want an editor in which to write Python code and run Python code, right? So you should think of Python as like English. It's a language. But just because you know English doesn't mean on your computer you have a way to write English. You have to download Microsoft Word. Microsoft Word is an editor in which you can write English, and it does extra little fancy things to help you write, right? Same thing with Python. We need an editor in which to write Python, and something that will kind of help us out with how it writes it and also run the code, and that's important. A third thing that we're going to take a small piece of advantage of today is that Python is very smartly built, in the sense that what you don't really want for a programming language is for it to be some gigantic, massive thing, right? So most all programming languages, most try to build in the sense where they have a core language that knows the essentials of what you need. But any specialty topic is handled by an external library, meaning it's code that's written by some other people, and then you get to take advantage of that code. One of the important things is that a bunch of mathematical functions aren't built into Python. Even computing like the cosine of 30 degrees or something like that, there's no way to directly do that with just the core Python language. But there are some incredibly good libraries that have been written by a ton of nerds that are all way smarter than all of us, that you can import that library and say, hey, let's use this library to compute the cosine of x. Let's use, even the number e is not natively known by the core of Python. We have to get that kind of information from a math library. So we're going to use one additional library. And the other cool thing about this particular download of Python, the Anaconda download of Python, is that it comes with the core language. It comes with a variety of editors that we can use. I'm going to use one of the editors that comes with this Anaconda installation of Python here. And also, it comes with like 100 of the most commonly used libraries so that you don't need to like individually download one and connect it to your Python install and all this kind of really annoying stuff. This is like one total package download and install right here. So if you're interested in following along with us here with the Python programming version of these things, then you can come to anaconda.com/product/individual. And that will take you to where you can download this guy. And again, the Anaconda installation of Python. Anaconda is just referencing this like broader package that gives you like kind of all the parts that you need rather than downloading Python, downloading an editor, downloading individual libraries. That's kind of a chunky way to do things. And this has it all wrapped up into one tight bundle here. So I would recommend that you do that. But again, not required, but highly recommended. You should do this. So let's pop back over to Word here and kind of start, as I kind of said here, let's cruise through the easy ones. And again, I know that every one of you have already seen these first two right here. So I don't expect there to be any confusion. I expect us to be sort of reminding ourselves of where we're at. I expect us to be able to translate this. I expect you to be able to, even if you have never seen any lines of code in your entire life, I absolutely expect that when you see the Python code that I'm about to write, that you're going to look at that and say, I totally see how that's exactly performing the computations that I know are associated with the left and right hand rules. All right. So I think that the other good part about today is that I think that this is honestly a really good introduction to programming if you've never written code before, because all we're trying to do is do a bunch of fancy multiplication and addition and use some function notation. And that's all that's really going to happen in our Python code. So I think that all of you are really going to be able to follow along with this. Otherwise, I wouldn't be doing all the Python within this video here. So I would recommend you pause and download and install and then carry on here. So let's cruise through the four easy ones. We're going to do all five of these in this order right here today. So we're starting with the left-hand rule. This is the first Riemann sum you ever did. I know that because I looked in the textbook and they show the left-hand rule before the right-hand rule in section, I don't know, what is it, 5.1 or 5.2 or something like that. To estimate the value of the definite integral from a to b of f of x dx, we subdivide the interval from a to b into n subintervals, and we determine the areas of the rectangles whose left corners, upper left corners, touch the curve. Notice in this picture right here, I have the left, the right, and the midpoint rules all in one picture just from some nice image I snagged from the internet. I'm going to copy this picture into our next two sections because the next two are right and midpoint coming up right here. So we're looking at this picture right here. Our left endpoints are the ones that touch the curve. That's why we call this the left-hand rule. So what you guys know is that when we're doing these types of approximations, you are always given the interval a to b because that's the bounds of integration over which we're attempting to approximate this integral. You're also informed of information like how many subintervals. So we refer to this usually as like the L6 approximation would be the left-hand rule with 6 subintervals. So what you know, and again, I know that most of you have forgotten the technical details of this, but I expect that everybody recognizes the parts that I'm coming up with here and says, oh yeah, a lot today. What you know is that based on your information of the upper bound, the lower bound, and the number of subdivisions, n, we can compute the width of each of our rectangles. Delta x is the width of each rectangle. Right? So based on this delta x, we can come up with the list of all of the x locations of interest. And I know this is really small on your screen right here, but these x values on the x-axis here start at A and end at B because that's our interval of interest. And we label each of the in-between values. Notice that these three in between are labeled x1, x2, and x3. What that means to me, by the way, is that A is the same thing as x0, and B is the same thing as xn. Here there are 4 rectangles, and x sub 4 is the same thing as B. So x sub n is what I might generally refer to my B as here. So let me just kind of note this over here for notational purposes. And again, kind of the biggest challenge of today is just being smart with your notation, right? The math of today is easy. The organization and the performing the mountain of computation is the challenge, right? So what we recognize here with our left subintervals, the important thing that I notice here is that my final rectangle in my left-hand rule, its location where it touches our curve right here is actually not at B, right? This B value, we never actually use its height to compute the height of a rectangle. Notice in our right-hand rule, we do use B. And notice that in our right-hand rule, we actually don't use A. Does not correspond to a curve height on the right-hand rule, right? A does correspond to a curve height on the left-hand rule here. So what I want you to notice right here is that the function evaluated at a is our first value. So that's the first value in my x list. And again, this x list is specific to the left-hand rule. The final value in my x list is not the nth, is not a with n additional delta x's. It's with n minus 1 because we didn't quite get to the last one out here, right? Our left corner is the thing of interest right there. So we got to x3 instead of x4 for 4 subdivisions. So here, this is sort of like saying x0, x1, x2, and x3 are the 4 x values of interest to us. So notice there was sort of that off by 1 error right there, considering that we start at x sub 0 for our counting, right? So if we want to estimate the area using this x list, and by the way, in Python, this is exactly what we're going to do, is we're going to say we're taking in a, b, and n into a function. We're going to compute delta x based on a, b, and n. We're going to generate the desired list of x values that are of interest to us for that particular approximation. We're going to use that x value list to make our area estimate by adding up the heights and multiplying the sum of the heights by the collective delta x right there, because that width is always constant, right? So notice that this computation right here is exactly the area of the first rectangle right here. The width of the rectangle is delta x. The height of the rectangle in the left-hand rule for the first one is determined by x sub 0, also known as f of a right here in this case, right? And again, notice that we only go out to 1 before the last value. We don't quite get to b with the left-hand rule. You guys know what the transition is going to be when we go to talk about the right-hand rule in 5 minutes here, is that we're going to not include the firsts because we recognize that a does not correspond to a height for the right-hand rule, but we are going to include the missing last one because the last one is associated with a height according to the right-hand rule. So that's the only transition between the left and right-hand rule. Left-hand rule does include the first and doesn't include the last. Right-hand rule does include the last, but doesn't include the first. It's the only difference between them, right? So we notice that this is just the height of a rectangle, and then the height of the next rectangle, and then the height all the way out to the last rectangle that we have. So that's rectangle plus rectangle plus rectangle plus rectangle all the way to the end. What we're recognizing is that every single one of these multiplications has a delta x in it, meaning we can factor that delta x out to the front, and all we have left over is simply the sum of all the heights where we intersected the rectangle. So there's 4 height value. I have the first one and the last one. You can see the other 2 sitting there. It's the sum of the heights. And we're going to want to start getting pretty dang comfortable with our summation notation because all chapter 11 is going to deal with summations out there. So this is something we should kind of get used to right here. That capital sigma symbol says add some stuff up, and that is basically our discrete version of an integral right there. It says add up all of the heights, f of x sub I, where I starts at 0 and goes up to n minus 1. Then take the value of that sum and multiply it by the width, so that this actually now, instead of just being an addition of a bunch of heights, is height times width, height times width, height times width, if we were to distribute that delta x back out there. And we generally denote this as the left-hand sum with n subintervals. So L sub n is our typical like super abbreviated shorthand for this type of sum right here. So again, what you guys know is that when we go to talk about our right-hand rule in a minute, the only thing that's going to change is the subscript on the x sub I right there, because instead of starting, notice here, we start at I equals 1. When I plug in 1 for I, that really tells me that x sub 0 is the first x value of interest. When we go to do the right-hand rule, you know that x sub 1 right here is going to be the first height of interest. It's the first right-hand corner that touches the curve. So the only thing that's going to change in a minute when we get to our right-hand rule is we're just going to have x sub I instead of x sub I minus 1. We're shifting either to the left or to the right relative to the other sum, the left or the right-hand rule, which x values we're interested in. So what I want to do is I'm going to pop over to Python now, and I'm going to write some code because coming up we're just explaining the right-hand rule again. So let's kind of do these kind of adjacent to each other here. So here is what I would like to do. So what I'm going to do is I'm going to open up the editor that is associated with writing Python code, my preferred editor for Python code here. And that is what is referred to as Jupyter Notebooks. It's one of the things that comes with this Anaconda installation right here. So I'm going to open Jupyter Notebook from the thing that I got from the Anaconda install. One important thing is that this Jupyter, this thing is a little bit unique as compared to other things in that it's not quite like most other editors for programming languages in that As you can see, it exists in browser, which is a little bit weird, right? This thing just opened up, this Jupyter thing just opened up in my browser up here, which is a little bit odd. The other thing that happened that you can't see, but just happened, is a black window showed up on my screen with a bunch of stuff. Depending on your age, you may recognize from the ancient age of computers of sort of like a black terminal window that's got a bunch of stuff in it that you don't recognize. That's opening up a local like simulated server on your computer that handles a lot of our Jupyter interactions. It's how Jupyter talks to Python. And so if you're following along here with that, when that black window opens up, don't X out of it. You can minimize it. You never need to touch it. But if you close it, then this stops working and you need to reopen it again. And so leave that available to you here. So I'm going to go to my Math55 stuff here, and I am going to open, I think that I want this one right here. No, that's not the one I was looking for. And so notice here, by the way, all these files are IPYNB. That stands for Iron Python Notebook. This Jupyter project is the original version of it, like 20 years ago. It was originally called Iron Python. They changed the name to Jupyter when they decided that this style of code writing, they wanted to work for more things than just Python. So Jupyter is actually an acronym that stands for Julia, Python, and R, which are three of the most used math and statistical programming languages out there. So lots of scientists use Julia, Python, and R as their programming language here. So where's my oh, that's because I went to the wrong class. Duh. Okay, now let's go to the actual correct thing right here. And let's grab this notebook here. So let me make this a little bit bigger here for us so we can see. So here's what we're doing here. Today we're going to approximate a bunch of integrals, right? So let's check out the left, the right, the midpoint, trapezoid, and Simpson's rule for estimating integrals. What you know is that for all of these rules, we need to know the interval of approximation, a to b, and we need to know the desired number of subintervals, n. Let's estimate one integral that we can do directly so that we can compare answers. So that's going to be our f of x equals x cubed over the interval 0 to 4. So we're just computing this integral here. The other one that we're going to do is one that we have no antiderivative for, so that we can kind of see some estimates. I mean, this is half the point of all of these approximation rules, is saying if something doesn't have an antiderivative, I still want to be able to come up with estimates for its definite integral value. Even though I can't do the calculus, I can still do the geometry, right? So this f of x function represents one that we can do by hand. And by the way, super easy. Honestly, I expect that half of you guys should be able to do this in your head. The integral from 0 to 2 of x cubed is 64, right? And we can do that. So we're going to know an answer that we're going to expect to see when we do these ones. Here we have no idea what to expect from these integrals right here. No antiderivative exists for that function. So for this one, we're going to just rely on our estimates to come up with values, right? So these are kind of the two examples that we'll follow in the code that we're going to write here today, right? So let's write a bare smidge of code here. And the thing I want to do to start right now is, before we even start writing, notice I gave myself some room before we get to the left-hand rule, is I want to write some Python functions that will exactly compute these values for me. All right. So what I'm going to do is I'm going to write these two functions here. But one thing that's important that I told you guys a moment ago is that Python doesn't even know the number e, right? So what I need, one thing I need to do first is I need to bring in one of the libraries that came with the Anaconda installation to use that to help us compute some e values here. So first thing I'm going to do is I'm going to bring in that external library. So I'm going to import NumPy. NumPy stands for Numerical Python, and it's the name of a honestly, NumPy is like a huge, huge deal in the science world out there. It's the reason why Python right now is the fastest growing programming language on earth, and is, I think, like the #2 most used programming language worldwide right now. It's grown an absolute ton in the last like 5 to 10 years. And one of the major reasons why is very specifically the NumPy library. It is so dang good at doing so much like math and science related stuff that there's just a ton of support for these things that are pre-existing. We're going to use an absolute bare tiny smidge of it just to compute e to the power of, and that's all we're going to use it for. But like, man, if you're familiar with like MATLAB, NumPy alone as a single library within Python, I think is quality enough that I don't know that MATLAB even needs to exist anymore. Like, it's destroying entire programming languages, this one library right here. It's really powerful stuff. One thing though is that people generally don't use the full name NumPy, even though it's only 5 letters long. Oh, do I have the wrong thing right there? Yes, thank you right there. Oh, and now you get to see some of the code that I wrote for this, by the way. The question in chat was that I have an error right here in my thing right here. I said from 0 to 4, and I totally want this to be from 0 to 4. So I'm going to make that from 0 to 4 right here. You should see, by the way, that what I'm doing right here is I'm writing a little bit of LaTeX code. An awesome thing about these Jupyter notebooks is that in markdown cells rather than code cells, you can write this. These markdown cells will take regular old English. They'll deal with headers with our pound signs up here. I can make that thing get smaller by doing different sized headers out there. It interprets HTML if you know HTML, and very importantly for me, it interprets LaTeX. So I can write some like code right there in LaTeX that is going to produce some math typesetted things right there. So now I fixed it. I said 0 to 4, but my integral had said 0 to 2 right there. So thank you for that catch right there. So I'm going to go ahead and import NumPy, but a typical thing that people do is abbreviate this a little bit so that we don't have to use the full word NumPy right there. So it's incredibly common for people to shorten that to NP. And Python has a special little keyword as that will allow you to sort of rename a library's name so that every time we ask for NumPy to do something for us, rather than typing out NumPy, we can just type NP, and that's a reference to the knowledge from this library. So you should notice over here it says in, and there's nothing inside of these brackets right here. I'm going to press Shift Enter, and that's going to run this cell. It's going to evaluate just the line of code that I have in this cell. Alternatively, I could click the Run button right there, and it would run, again, just that one cell of code right there. So I'm going to Shift Enter, and for one brief instant, it showed an asterisk right there while it was thinking, while it was bringing in all the knowledge of that library, and then it changed it to 1 to show me we've successfully completed this, and this is the first cell that's been run here. So again, what I want to do is I want to define our functions of interest. So let's write a little bit of Python code that's going to essentially define these functions and name them f of x and g of x here. So to define a function, we use the Python keyword def. Def will say define a new function. And this works exactly like function notation. I'm literally going to define this as f of x. I need to use a colon here to indicate that I'm going to describe how this is defined. When I hit enter here, you should notice that by default, this has indented you in by 1 tab. Python really cares about spacing being according to some important tab indentation rules right here. And that's to help people be able to read your code. If everything was just all vertically aligned, that's not helpful. You should think about like smart note-taking strategies where you sort of like maybe like indent bulleted lists, and then like a sub-bulleted list would be even indented further. That's exactly how everything is going to get written in Python here, and we'll see a little bit of that here today. So we want to define this f of x function. It's a really simple function, right? We just need to do one computation. So all we want to do is return, and by the way, notice as I'm typing RET, it's in black right now, and watch, oh, it turned to green because it became recognized as a special keyword in Python. What do I want to return? Well, if the f function takes in x, what I want to return is x cubed. Tiny little detail right here. The up arrow caret right there is not the power indicator, exponentiation indicator in Python. It does a different thing with bitwise operators, a binary number modification. Double asterisks is how we indicate exponentiation in Python here. So there's my f of x function. Super simple. Define the function f of x. What should it do? It should take its name is f, that's in blue. It should take in one variable x, and it should spit out the value x to the power of 3. And I also want to, and I can do this in the same cell if I want, I also want to define my g of x function. This one will be ever so slightly more complicated because it's e to the power of x squared here. But similarly, it's just like one computation, right? So I'm going to return, what do I want to return? I want e to the power of x squared. So E is not natively known to Python, so I got to ask the NumPy library. I got to say, hey, NumPy, can you hit up E for me? And it'll be like, yeah, man, I got you. And so I'm going to do NP, that's saying, hey, NumPy library, please, NumPy library, do your exponentiation function, right? So np.exp, this is what gets us e to the power of. E to the power of what? That's what goes in the parentheses. We want it to the power of x squared. So that is e to the x squared right here. And I can put this as a comment right here, e to the power of x squared right there. And maybe I'll do some like parentheses right there so that's a little bit more obvious, right? So again, this is me saying, asking the NumPy library to do me a favor. And since I'm asking the NumPy library, you can explicitly see me saying that I'm asking the NumPy library to do that exponentiation for me. So again, these functions are not yet known because I haven't run this cell yet. So if I try to do like f of 3, it would get confused. But once, and in fact, let me just do that to show you f of 3, and it's going to be like, oh, f is not defined over here. That's because I never ran this cell to let it know what f and g are. I just typed it, I didn't run it. Now I'm going to shift enter in this cell. You can see that now the numbers there, this has been determined. I know that f of 3 should be 27, and it looks like we are getting 27 right there. So you should be satisfied about that. Let's also double check. Let me just kind of say here so I get my comments. So notice, by the way, I switched to a markdown cell so I can write a little bit of English. That's the reason I really like these Jupyter notebooks, is because you can write a little code, write a little English. I can use LaTeX to write a little bit of math, and then I can go back to writing code. You can kind of keep on interweaving. It's really nice here. So confirming that they work as intended. I'm pretty confident about the f function right here. We can do 4 and C64. It seems to be working right there. The other thing we can do here is we should check out this g function. Now this one's a little bit weirder right here, so I'm going to check a variety of values. So g of 0, what should that be? Well, g of 0 should just be e to the 0, so I should get 1 for that guy. If I did g of 1, that should be e to the 1 squared, which is just e to the 1, so I should get the decimal representation of e. And to check and make sure that the squaring is going to work up there, we can do something like g. And if we do g like 2, I know that that should be the same thing as e to the 4th because it's e to the 2 squared. So if I run that, it gave me back 3 values and exactly as we expected. G of 0 is 1. G of 1, that's that decimal that you recognize to be e. I definitely don't recognize that decimal, but I can compare it to np.exp of 4 and see that I am getting, in fact, the exact same right there. So g of 2 does match the NumPy's version of e to the power of 4 right there. So I feel pretty good that my f and my g functions are doing the job that I wanted them to do here. So we'll reference f and g a bunch throughout our code here today, and they're always going to be referencing the x cubed and the e to the x squared code. What we want to be doing is approximating areas underneath these curves right here. All right, so we've defined our first functions in Python. All right, so now what we want to do is we want to define our left-hand rule right here. Since we're going to want to use the thoughts behind this left-hand rule over and over and over, I don't want to have to write my same code over and over and over. So just like we defined the f of x and g of x mathematical functions here, I want to define some more general programming functions here that do a series of operations for us. So just like we defined a function above, but it was purely a mathematical function that just performed one computation, we're going to define some functions for all 5 of our rules today, but they're going to involve lots of lines of code because as we saw in our Word document, there's lots of steps to this process here, right? So I'm going to go ahead and define our left rule is what I'm going to call it. And what type of information are we going to need to know? If I'm just saying, hey man, I want you to find this left-hand approximation. Well, you should be saying, I need more information than that. I need a lot more information than that. Um, and what information do you need? Well, that's all the stuff that we're going to put as our input into the function. If I just said to you, hey man, perform the left-hand rule, you should be saying things to me like, what function do you want me to perform it on? I'll call that func as one of our inputs right here. We need to know things like what interval of interest? Well, A and B would be the bounds of the interval of interest. And another thing I need to know is how many subintervals do we want to break this thing down into? So these are really the 4 pieces of information. You should notice, though, this is still exactly the same thing as every bit of function notation you've ever seen in your life. I'm just using a word for the function name, and I'm giving names to the 4 pieces of information that are coming in. Instead of just like an X and a Y, I'm kind of describing them to myself a little bit right here, all right? And again, these names aren't like special. I'm giving these just as guides to me. It doesn't matter what those names really are to Python. We could call these any kind of gibberish we wanted right here. The point is this function is going to expect to know these variables to do all the computations on the inside. So real quick, I want to pop back over to Word here, and I want to remember where we're at. In Word, what we're seeing over here is that the first thing that we want to do is compute delta x. And we know that we can compute the width of one rectangle as the overall width, b minus a, divided by the number of subintervals, n. So let's do this as our first computation in Python as well. So I'm going to pop back over to Python, and let's do exactly that. I'm going to go ahead and first I'm going to compute, and I'll call this variable dx for delta x right there. And what it should be is b minus a over n. That's all I'm going to do, right? I mean, that's literally exactly what the math is. I'm calling it dx for shorthand right here. Remember to keep in your mind that dx mathematically is the infinitely short distance. That's not what we're doing right now. Delta x is our like finite measurable distance. This is delta x right here. I just don't want to have to type out delta every single time I use this guy right here. So I'm going to call it dx for short right there. Right. What else do we need? Well, and again, I'm just going to follow exactly what we were doing over here in Microsoft Word. So back in Word, the next thing we did is we came up with a list of the x values that were of interest to us. We know the list is going to start at our a value, and it's going to go up to, but not including our b value right here. So what I want to do is I want to literally make a list in Python. I'm going to literally call it x list, and it should contain exactly those values right here. So let's go ahead and do that. So next up is I want to make a x list here. So I've got my delta x. And notice that I need my delta x to compute my x list. So I'm going to say x list. Lists in Python are indicated with brackets, not with parentheses. So notice those are square brackets right there. And what I'm going to do is I'm going to describe the list. This is a really powerful list making thing that Python can do that other languages cannot. I'm literally just going to describe what I want the list to look like. All of the objects that are in this list, what they should look like is they should look like, and I'm going to keep on doing this popping back and forth here. Back over here in Word, you should see that what they look like is it looks like we want A plus some number of copies of delta X. So the format of every single object in this list is like A plus I delta X. All of the objects look like that. The first one, that's A plus 0 delta X, all the way up to A plus n minus 1 delta X, right? I'm exactly going to form that structure here in my Python code. So what I want the objects to be in this list is they should look like A. And again, A is known because it was brought into the function. I want to do plus, and I'm going to do I times dx. But the point is here, we don't know what I is. We need to now tell it. We're kind of introduced. I has not been described yet, right? Well, what is I? We're going to do this for each I in, and we're going to do the range of n right here, right? This is going to say in the range of n. So if n is 10, this will give me for I 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you should notice that that's perfect. It actually automatically discludes the 10th value. Python is a zero-based indexing language. So when I do things like list range 5, it gives me the first 5 numbers that there are. 0, 1, 2, 3, and 4, right? So this is going to be perfect for us for these I values right here. But these are going, and in fact, I think what I should do is I'm just going to add this in as a little blurb right here so that you guys can see. But that's how that range function works right there. Add some cells here. So this X list should be getting me the X values that are of interest to me here. And maybe what we should do real quick here is let's just double check that this X list works. And by the way, I'm going to sort of like really go into detail on this one, and we're going to see we only have minuscule changes to make for all the rest. So this is sort of my one long form explanation. So this is not really what we want to get out from the left-hand rule, but this is my I'm checking my work as I go. Let's see, do I get the right X list here when I do this? So let's do our left rule. What function do we want? F, although it's not really used here yet. A and B, we could do like 0 and 4. And if we did 16 subintervals right here, then, oh, look, these are all the X values. So what it gave me back was my X list. And this is exactly what you know should happen. If we're going from 0 to 4 with 16 subintervals, then it should be a 1/4 width as our delta X. And I am seeing starting at A, which is 0, and going up to, but not including B down there. So I'm pretty satisfied with the X list that I just generated right there. It does count by quarters as it should. It does include A as it should. It does not include B. It goes up to 1 before B as it should right there. So this X list appears to be exactly the X values that I was actually interested in here. Now, that's not what we're going to want right there, but that was I checked my work with that right there. What I really want from this is I want to compute my Y list, right? So again, popping back over to Word to see what we're doing over here. From this X list that I generated right here, this is my X list that we just created. What I really want to do is I want to create this list of the corresponding Y values, right? I don't just want X0 through X sub n minus 1. I want F of X0 through F of X sub n minus 1. Once we build this as a list, we can sum them all and then multiply that value by delta X, and we're good to go. So let's build a Y list. Let's take the sum of the Y lists, and let's multiply the sum of the y lists by delta x. That's exactly what our formula says right here. Right? So let's go ahead and do that. So now that I have an x list, I can build a y list from it. So here, similarly, I'm going to describe all the objects. What do all the objects look like? Well, they're all going to look like our function being applied to x. And I'm using func here generically. Remember that we're going to give it in the func slot right there, either f or g, and then it will either do f of x or g of x correspondingly right there. I'm using this as a generic function placeholder. When we apply this left-hand rule Python function, we'll be giving it which mathematical function we want it to use in that slot right there. So I want to apply whatever function we're looking to estimate to an x value. Which x values? For each x in the x list. We want to do the function applied to x for each x in the x list. So x is sort of our dummy variable there, holding in. It's going to loop through all the values in x list that we just created. It'll think individually as each of them as x for a moment, apply f to that x or g to that x, and give us the corresponding y value. So this is going to be our corresponding list of y values. And now we can use this to compute our area. Our area should be dx times the sum of the y list. Again, I think that's a code that, man, if that area line of code confuses you, then you're in trouble. Delta x times the sum of the y values. That's exactly what our left and right hand, and honestly our midpoint trapezoid rules are doing as well right here. What do I want to get out as my final answer? The area. So there we go. We've built our left-hand rule function by using a, b, and n and the function to compute what's delta x, what x values do we use for the left-hand rule, what are the y values that are corresponding to those x values, and how do you compute the area knowing the y values and delta x? And then saying, give me the area when you're all done. So I'm going to go ahead and run this block of code here. And notice, this output from left-hand rule that we're visualizing right now is wrong in the sense that it's actually x list that we're seeing here. What we really wanted was area. And so let's see. Hey, so we knew that our answer should have been for this guy 64. We just got the answer of 56.25. But wait a minute, that was, oh yeah, 0 to 4 of x cubed. Okay, so my question is, if we increase our number of subintervals, do we get closer and closer? Ooh, we're getting closer right there. Let's do one more thing to watch it like approach this value right here. So I'm going to do a for loop here to do some repetition of some code. For I in range, and so remember that we saw this thing right here, that when you do range, it actually starts at 0 and it goes up to 1 less than the value that you actually threw in right here. So I'm instead going to start my range at 1, and let's go up to like, I don't know, 21 or something like that. What I want to do is I want to see what is, and I'm going to do 10 times I. So instead of looping through the values from 1 to 20, this is going to get me from 10 to 200 because I'm going to do 10 times that I value. And what I want is I want to get my left-hand rule approximation using the function f. A value is 0, b value is 4, and how many subintervals? Well, that's what I'm going to do my 10 times I as right here. And when I run this, what this is going to do is it's going to show me if you approximate the area underneath f of x equals x cubed from a equals 0 to b equals 4, this is showing you if you use 10 subintervals, here's our approximation. 20 subintervals, here's our approximation. What we can see is happening here is we can see that these values are getting closer and closer and closer to 64. We can see that every single time we increase our number of subintervals, our estimate gets better and better and better. We can see that we're approaching from below. I'm going to go back over to Word and show you how I knew that that was going to happen. In our diagram over here in Word, we are also looking at an increasing concave up function right here. And what we can see is that the left-hand rule is always going to be an under approximation of the area when we're doing when we're looking at a concave up function that's increasing right there. We're always going to get underestimates. So all of our left-hand rule approximations are certainly underestimates. In a second, we're going to do our right-hand rule, and we're going to expect to be coming down from above, honing in on 64. So we're going to see some 65s and some 66s for our estimates out there. All right. And so let's just see that we can get kind of like really close with this in a sense if we want, that if we just make that x value huge, then we're still kind of getting the stuff that we want. So let's do one more right here. And let's just do our left rule with f from 0 to 4. And let's just do like a huge number. And again, this is really nice. I can do 100,000. In fact, let's just do 1,000,000 right here, 1,000,000 subintervals right here. Watch how long this is going to take Python. Oh, essentially no time whatsoever right there. You can see it paused for a brief second right there. This did take it like a tenth of a second to do that instead of like a negligible amount of time. But we can clearly see here that with a million subintervals, we've basically arrived at our 64 right there, right? We've got a really, really, really close estimate right there. So I feel really good about the code that we've written right here. It's doing all the things that I anticipate this left-hand rule to do, all right? So the next thing we want to do is we want to do our right-hand rule. The code is going to be really easy because we're going to be able to basically just copy and paste this stuff and make some absolutely tiny edits to it right there. So let's flip over to Word and see what our little difference is right here. And again, I basically already verbalized all of the differences here. Right hand rule. This is the second Riemann sum you ever did. To estimate the value, we subdivide the interval a to b into n subintervals to determine the area of the rectangles whose right corners touch the curve. So now our rectangles have their upper right corners touching the curve. This is equivalent to using all but the first, right? So notice that our left endpoint rule, I guess switching back and forth here. Our left rule started at A, but did not include B. Here we are not including the A. A doesn't correspond to any of our heights of interest, but B does correspond to one of our heights of interest. So we still compute delta x the same way. We still want to compute an A list, but notice the list doesn't include A. It starts right away at x sub 1, 1 delta x later than where A is, and it does go out to B. Right? This is B right there. Right? So our x list before looked like x sub 0 to x sub n minus 1. We've just shifted the list over by 1. Now we're starting at x sub 1, and we're going all the way up to x sub n. The area estimate, identical structure right here. First rectangle, second rectangle, out to the last rectangle out there. We're going to say, oh, what do you know? They all have a delta x, so we factor out the delta x. We still are going to get a sum of y values right there. Once we sum the y values, we multiply them by delta x. And notice here's our summation formula right here. You should notice that the only difference with our summation formula here is it still goes from I equals 1 to n. Let me scroll back up. I equals 1 to n, just like below. But here, when you plug in I equals 1, I minus 1 gives you 0. So f of x sub 0 was the first height. Over here, when you plug in 1, you get f of x sub 1 as the first height right there. So the only difference in these formulas is literally that subscript is either I minus 1 or I, depending on if you want the left group of n chunks or the right group of n chunks out of the n plus 1 total numbers. Notice that if we do 4 subdivisions, there's actually 5 total x values that we consider. A, x1, x2, x3, and b. That's called the fence post problem. If you want to build a fence with four flat pieces of fence, you really need 5 fence posts to hold up those 4 pieces of fence. And so there always ends up being people that experience a little bit of this off by 1 confusion when we deal with these sums here. It takes 5 x values to denote 4 sub intervals. Stop and say that sentence to yourself for a minute and convince yourself that it's true. Let's go modify our old Python code and essentially repeat what we just did over there. So back over here in Python now, I'm just going to copy and paste straight up to get over there. So copy. Let's come down to our right-hand rule. The only thing we should change is to exclude the first value in the x list and include one more at the end. So that's the only modification I'm really making here. So I'm going to change left to right. I'm still starting by computing delta x. The only change that we want to make is the x list. Right? The y list is still just our function being applied to each of the x values of interest. Our area is still adding up all those y values and multiplying by delta x. We still want to get out the area at the end. The only thing that's changed, and this is even the structure of everything that's within the x list. The only thing we want to change is rather than going from 0 to n minus 1, which is what we saw that this did, right? Range goes from 0 up to the input minus 1. We instead want to go from 1 up to the input. So I'm going to start it manually at 1 and go up to, when I do n plus 1, minus 1 makes that n being the last value of interest. So that was the act of me shifting our indices over by 1. I increased the lower indice by 1. I increased the upper indice by 1. So it just shifted our x value indices over. That's the only modification we got to make. We still want to compute the y values associated with these x values that we've got now. We still compute the area by adding up the y values and multiplying that sum by delta x, and we get an area back. So I'm going to go ahead and run this block of code right here. Remember that what we're expecting for this x cubed function is that we expect to see all over estimates now, right? We see that we have extra rectangle above the curve, and that in this case, again, is just because this is an increasing concave up function right there. It's different for other functions, but in this x cubed example, we do expect to get an overestimate. So I expect that as I increase my number of subintervals, the rectangles get skinnier and skinnier, better approximating the area underneath the curve. But I expect our approximations to start from above 64, the known correct answer, and to converge down to it, rather than being below 64 and moving up towards it. So let's go ahead and see if that is in fact what is happening here. So I kind of want to do these same types of things right here. In fact, again, I'm just going to copy and paste this right here. Let's just go ahead and grab this guy right here. And I want to look at, again, now the only thing I need to change is left to right. And now we can see exactly what we thought. If you only use 10 subintervals, pretty terrible estimate. We know that the answer is 64, we're getting 77. But we're seeing that as we increase our number of subintervals, we're getting better and better and better approximations, and they clearly are not super clearly, but it looks like I could believe that they're honing in on 64 right there from above, exactly as we expected, right? Very cool. Let's again kind of copy and paste our do it at a million to see if it's actually what we think it's going to be. I'm expecting to get like 64.001, right? Something just barely above 64. Even better than I thought, 64.0001. I was off. We had a whole extra significant digit of zeroness right there. That was really good, right? So it looks like our code for our right-hand rule is good. We barely modified anything to make this guy happen, right? So next up, midpoint rule. Let's hit this guy. What is different about the midpoint rule? Now, I expect that every single one of you have already seen left and right hand rule before. Depending on what you did in 50A, maybe you skipped the midpoint rule. I know that when I made my video for sections 5.1, 5.2, 5.3, the first video I think you guys saw this semester, I skipped this one kind of because I knew that I was going to hit it now. And so in the midpoint rule, what you can see in the picture is that we're doing sort of the same thing as the left and right sums, but instead of finding the left corners or the right corners, we want our curve to pass through the midpoint of each of our rectangles right there. So if we're still getting all of our same, and again, I know this is tiny right here, but this A, X1, X2, X3, and B, we're still using those 5 X values on the X-axis, but what we're really interested in for our true X list is the halfway points between each of those 5 values. Since we have 5 values, there should be 4 total midpoints between those pairwise groupings of 2 values, right? So we're still going to compute delta x the same way. But importantly here, what I'm going to do is I'm going to get all of the x endpoints. And remember the fence post problem here. This really includes one more endpoint than we have subintervals. This is L4, R4, and M4 right here. But really, there are 5 x values that are associated with that, the endpoints of those intervals. So notice that this list right here is going to go, I highlighted that wrong, it starts at A, and it does go out to B. This is adding n copies of delta x to A. That does get us to B, right? So all x endpoints got us from A to B, right? All of it is included in there. But those aren't the x points that I want to use. I'm just trying to build my list for this is me showing my work right here. The values that we actually want to use for the midpoint rule are going to be the averages. So what I'm going to call x bar 1 is the average of x0 and x1. X bar 5 is the average of x5 and x4. It's the midway point between the two, so we can find those as averages right there. If we can get all these midpoint values right here, then once again, our area estimate has nothing exciting going on with it here, right? Hey, tab in, you jerk. This is still just the area of the first rectangle, the area of the second rectangle, the area of the last rectangle out there. We recognize that they all have the delta x, so we factor out the delta x, and we just get the sum of the heights of the midpoints, where the midpoints is the average between two of our x value endpoints right there. And again, we get essentially the same function notation here, but it matters that since we're describing our x values as x of I bar, that we sort of define what do we mean when we say x bar. Notice that it could have been that when we said x, for example, x bar sub 5, that could have been averaging 5 and 6 or 5 and 4. we kind of could have defined it either way, and things kind of could have worked out with slightly different notation on our indices. Because we chose this way, we want to kind of specify this way. So it matters kind of that I define what I mean by x bar, since I used x bar in my formula right there. But this, again, doesn't seem too far off from what we already have been doing in Python. It seems like the one difference is that we're going to want to build one list previous to our used x list, right? So my x list is going to be the averaged endpoints, but I'm going to build this list first, all the x values first. I'm going to use this list to compute the averaged x values. Then I'll use the averaged x values to compute my y values. I'll add up the y values, I'll multiply them by delta x right here. So adding in one extra little layer, but the structure to this is still the exact same thing. So let's go see it. Okay, so midpoint rule. We are looking at, again, very similar. This time, let's make a total x list that it goes all the way actually from A to B, and then find the pairwise average of each set of adjacent x values. So 0 and 1 will get averaged to make one midpoint. 1 and 2 will get averaged to make the next midpoint. 2 and 3 get averaged to make the third endpoint, stuff like that. Get rid of this guy here. Let's copy and paste some code from before. Again, I'm trying to just reuse a bunch of my code here. I don't want to have to reinvent the wheel every time. We want to change the name to mid rule. It's still going to take in a function, a, b, and n. We're still going to start by computing delta x. But I want to kind of change my naming right here. What I kind of think I now want is I don't want... X list to me is like the x's I actually want. And this is just names that I'm picking out by myself right here. So what I'm going to do instead is I'm going to call this all x. It's all the x values that we might want. And what we're seeing now is I want this... Notice that this one I copied from the right-hand rule. It was discluding the first. I want to include the first. So I'm going to start from 0 and go up to n. That's going to get me from A to B right there. So all x has all of them in there. Now what I want is I want our actual x list here to be the pairwise averages of each of these guys, right? So what does each object look like in the x list? It looks like the ith value from all x plus the I plus 1th value from all x, the next I value, I and I plus 1 is the two indices. I want to add those two together, divide by 2. That's exactly what I'm going to do right here, right? So I want, from the all x list, I want the ith value. And notice here that brackets serve two purposes in Python. Brackets say I'm creating a list if there's lots of things in it. Or from a list, since all x is a list, putting brackets on the end of it, it sort of looks like function notation. That's indexing out of the list. That's saying, give me the ith object in that list. I want to add that to all x I plus 1, the next object in the all x list, and I'm going to divide that by 2. I've taken the average of it. Now, what I need to describe is what were those i's. And what we know is that this can just be our I for in range n, I believe. And the reason that we can just go out to range, is this going to work? So if it was range n, and the largest value would be n minus 1, but then this would be giving me n minus 1 for I, and so that would be giving me actually n. But that would actually be one too many. I think I need to do right here, I'm going to change this so this is, oh no, I think that'll work right there, right? Because all x should have one more thing than what n is. So I think that's good right there. Cool. My y list doesn't change now, right? X list are the x values that we're actually using as our locations that we're computing our heights at. And so I'm going to go ahead and compute the function value at that x for each x in the x list. I'm still going to get my area by adding up the y list, multiplying it by dx, and getting an area. Now, what I know is that this midpoint, or this mid rule, should be, this is essentially we averaged all of our x values. So I'm expecting to get much, much better estimates much, much earlier, right? This is going to kind of mitigate the overestimate stuff from the underestimate stuff. Popping back over super quick before we actually run this, what I'm seeing in my picture here is it seems like the amount of overestimate that we're getting is not the same as, but is helping to cancel out some of the underestimate that we're getting, this missing gap that's right there, right? So I expect our midpoint rule to be much better with much lower number of subdivisions right here. So let's go back and see if we got everything right in Python over here. So I'm going to go ahead and I'm going to run this cell. Notice again, I can see that I've never run this cell, so it still doesn't know the midpoint rule. So I'm going to go ahead and run this. And let's go ahead and again grab our checking out a whole bunch of different cases here. And again, notice how much freaking work it's doing here. Every one of these is like starting over from scratch. It's got to rebuild dx, rebuild all of our x values, recompute all the y values, add them up, multiply them by dx, start over with the next line. Now do it with 130, now do it with 140, now do it with 150. All this is happening, in a sense, effortlessly. And especially if you're just kind of copying my code along here, then it's just, it is effortless right here. So I'm going to use my mid rule, and let's do the same thing right here. And here's the thing we should be noticing. Look how dang good that first estimate is with only 10 subintervals right there. I want to scroll back up real quick. Look at this. 10 subintervals, we were off by like 13 above. 10 subintervals, we were off by like 13 below. 10 subintervals for the midpoint rule, we're off by like 0.32. Right? The midpoint rule is doing a great job of mitigating the above versus that below, over versus underestimate right here. And we can see this is doing a pretty nice job. I mean, this is converging slowly, but that's because it's kind of like already there in a sense, right? 63.9992. So at 63 point, right. So this one at 200 was still quite a bit further off. Our percentage error here is quite a bit larger than our percentage error here. We're kind of nailing this thing by now with only 200 subintervals. And if we do the ridiculous thing and take this to the extreme and go a million subintervals like we did before, I wouldn't be surprised if this almost like just straight up gives us 64. Oh, oh, we're getting close. Nice midpoint rule. Accurate to like 10 decimal places of nines right there, right? 1, 2, 3, 4, 5, 6. Yeah, 10. We got 10 nines in a row. We're nailing it. So good job, midpoint rule. Midpoint rule is doing a pretty good job of compensating that our overestimates are approximately equal to our underestimates. And so by taking that midpoint, we're sort of like canceling them out a little bit right there. All right. So cool with the midpoint rule. Took us a little bit of extra work here that we had to get all the x values, not the ones that we're using, but all the way from A to B. The x list here was the averages, pairwise averages from all x. So maybe I'll add a comment here. So x list is pairwise averages of the values in the all x list, and I can see that right there. There's my average of the ith value and the I plus 1th value from the all x list for each of the indices going from 0 to n minus 1. And it has to only be to n minus 1 because when we do the I plus 1 right there, that's actually going out to the nth term out there, the final one that we're getting, right? Because that plus 1 bumps us one further for that average. You can't take the average of the last term and then one more because there's not one more after the last term. Cool. All right. Let's keep rolling here. Up next, we've got the trapezoid rule. Trapezoid rule. So in the trapezoid rule, and this is one, by the way, I don't expect anybody seen this, still just doing geometry. And importantly, notice that our graph has changed now. We're finally on to a new diagram right here. We're going to do something very similar, though, to the midpoint rule. In the midpoint rule, we averaged adjacent x values, then summed the area of the associated rectangles. In the trapezoid rule, we are instead going to sum the areas of rectangles with trapezoidal tops, right? Notice that in our diagram here, our trapezoid rule has a slanted top right there. You should easily be able to see by visual inspection that the area of one trapezoid rule chunk is the average of two adjacent y values that we see from rectangles here, right? So you should be noticing here that if we do this rectangle plus this rectangle, that the average height between the two, I'm going to say divided by 2, should be giving us, notice this corner, I'll call it A and I'll mark it A over here. This corner is B. I'll mark the B up here. Boom. So this is literally just the averaging of the y values rather than the averaging of x values. So that's The midpoint and trapezoid rule mathematically super similar. In the midpoint rule, we first take the pairwise average of x values, then use those averaged x values to compute our heights. Here instead, we're just going to take all of our x endpoints, compute all of the y values for all of our x endpoints, then take the pairwise averages of each of our y values. Those are the y values that we'll actually use. We'll add them all up. We'll multiply them by delta x, right? Midpoint averages x's, trapezoid averages y's. All right, so we're going to compute all x endpoints. We've already computed delta x. That's still a thing. You should notice the area of our first trapezoid is delta x, that's the width, times the average height of the first x value and the second x value, x sub 0 and x sub 1. You should notice that this is the average of the first terms, each in our left-hand rule and our right-hand rule right here. So consequently, we can find our trapezoid sum by averaging the left and the right-hand sums here, right? That's going to be our special relationship, is that the trapezoid rule is the average of the left and the right-hand rules. The midpoint rule didn't really get that for us because of the fact that there can be more change from x sub I to the midpoint than there was from the midpoint to x sub I plus 1. The trapezoid rule is going to truly get the average height between two y values. And so it's actually going to be the average outputs from these guys that are right here. So what you should see is happening here is that we are getting, and I want to kind of explain this little line right here. What we're getting is we're getting things like f of x0 plus f of x1 over 2 plus, so this is our delta x times, plus f of x1 plus f of x2 over 2 plus f of x2, x2 plus f of x3 over 2. And you should notice something special that's happening here. F of x0 only got written one time. So when I factored out the 1/2 right here, there's only one copy of f of x0. But all numbers in the middle get accounted for 2 times, right? There's 1/2 of x1, and there's another 1/2 of x1. And so we actually get 2 copies of 1/2 of f of x1 for all of them until once we get to the very final term, just like x0 only appeared once in our sum of averages, xn will only appear once in our sum of averages, the very last thing. It doesn't have a later partner to average with. And so notice the coefficient on this one is also 1. So in this way, in this sum right here, it's all 2's for the middle coefficients, for all the middle coefficients, but only one copy of f of x0 and one copy of f of x sub n. And you can kind of see it from writing this out as the sum of averages that it really is. x0 occurs one time. All middle terms get accounted for twice. And out there, f of x sub n once on the end out there. All right. So we can see this for the sum as to how this is going to get constructed here. And what you should see is that if you take f of x sub 0 through f of x sub n minus 1, that's L sub n. Then if you take f of x sub 1 all the way through f of x sub n, that's our Rn. And that's exactly where we're getting this from. So we're really getting here, L sub n is this guy here. R sub n is going to be starting 1 later and going 1 later. And so here you can see that we're doubling up on all the stuff in the middle. This is our f of x sub 0. This is our f of x sub n. And this is our doubled up. So you can kind of see here exactly how, like kind of a visual way that we're thinking about our left hand and our right hand sums right there, and how these guys are going to actually truly just average to give us this. So this is good because now when we go to write our code for this guy, we can check our answer by seeing if our output from the trapezoid function that we're going to write does give us the same outputs as the average of the left and right hand sums that we've already written in there, right? So let's go ahead and see if we can do our trapezoid rule right here. So notice that we need to get all x values, so we'll make an all x list again. we're going to want to get all associated y values, and then we're going to do the pairwise averages of the y values instead. All right, so let's go ahead and do that guy. Oh, one thing. Here we are. Here we are. Okay. Trapezoid rule. All right. Midpoint rule, we average adjacent x values. Trapezoid rule, we're going to average adjacent y values. This is the same as averaging results from left and right hand rules. I'm going to go ahead and grab my old code from the midpoint rule right here. Call this our trap rule. All right. So for our trapezoid rule, we're taking a function a, b, and n. I want to make my all x list, and that's going to be the same right here. I want to get my corresponding all y list as well, and then we're going to, instead of finding my, we're not going to need the x list anymore right there. Let's go ahead and get all y. All y should just be applying our function to the x value for x and all x. And now, just like we had, actually, sorry, let me go ahead and grab my, when we did the x list before right here, I just want to kind of mimic this code right here. Get rid of this y list, right? And what we really want is to generate the actual y list that we're going to use right here. And all I'm going to do is just swap out some x's for y's. I just want the pairwise average from the y list instead of the pairwise average from the x list. I think that's all I had to do right there. And again, now we just get our area formulation right there. So we found all the x's, all the y's that went with the x's, the actual y list that we wanted to use. And so now I can say here, y list is pairwise averages of y vals from all y, right? So very, very similar to what we did with the midpoint rule there. No way, this is annoying me. There we go. So let's do it. And importantly here, we get a little bit of a different check on this one. So let's do our usual checks right here, which is do this for a whole bunch of different subintervals and watch it converge on the known value of 64. Hey, we're getting some pretty good estimates right away. Again, 63.68. How does that compare to the midpoint rule? Ooh, it looks like for 10 subintervals, we were getting essentially the exact same thing. Interesting right there. And it converges. Wait, oh, I see why. Oh, how surprising. It's because I didn't change this to trap. No, I'm like, wow, those are the same. All right, here we go. Here we go. So 64.64. So we're 0.64 above. The mid rule was 0.32 below. I wonder if those numbers are related to each other. 64 and 32. That's weird. It looks like at the end of the midpoint rule, we're off by 0.0008. And here, we're off by 0.0016. It seems like our error for the trapezoid rule seems to be double the error from the midpoint rule. I'm going to make a note of that. Or wait a minute, is it... Zero 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 eight, which gave us 0.0016. Yeah. Okay, cool. Okay, so that's an interesting kind of takeaway that we can have right there. So let's go ahead and see, again, I want to kind of double check that I'm getting this average of the left and the right hand rules. So let's do like a single computation right here. Let's just do our trapezoid rule with maybe like 100 subdivisions. So our trapezoid rule for f from 0 to 4 with 100 subdivisions. Trap rule 64.004, and I should be able to do this with our left rule f0 for 100 plus our right rule f0 for 100 all divided by 2. I'm averaging the outputs from the left rule and the right rule, and oh, we're getting the exact same output as we got from doing the trapezoid rule. So it does look like, but with just a little bit of a experimental checking of some values here, we are in fact getting the average of the left and the right are giving us the trapezoid rule right there. All right. So we have now arrived at the one that we actually have to try hard for right here. The last four was really just kind of writing some Python code was kind of the challenge of it right here. because I didn't want to do any by hand math. Let's go ahead now and actually talk about some good maths here with the Simpsons rule. This one's going to take a smidge more effort here. All right. So those are the first four out of the five sums that we need to discuss. We still need to discuss error bounds. That's what we're going to do last. Hopefully your takeaway so far is we're just doing a bunch of basic geometry. There's no new concept here beyond the concepts of Riemann sums that you already had. By far the hardest part about this is tracking notation and being able to come up with a smart way for you to be able to do this computation, right? And again, using your TI calculator, using Excel, or copying my Python code here is something that you're going to need to be able to do for this section here. So let's go ahead and look at Simpson's rule, and then we'll go ahead and look at our error bounds for the midpoint trapezoid and Simpson's rule here. So in the trapezoid rule, we essentially decomposed a curvy function into a bunch of straight line pieces, right? The special thing that happened with the trapezoid rule is we started approximating with things by actually putting a curve that tracks the same curve, or sorry, putting a straight line that's actually tracking the curve that it passes through rather than strictly flat topped rectangles. So the trapezoid rule was an improvement in the sense that it's actually following the curve rather than just plopping down a rectangle. The Simpsons rule, you should notice, is actually a curvature of approximation right there, not a straight line. Right? So you can think of this as having found a sequence of linear approximations or first order approximations to the function, right? It's like saying if you have some curve in space, you could approximate it by drawing a bunch of straight lines that are approximately doing that curve. That's what the tops of your trapezoid rule are going to look like. What Simpson's rule is going to do is it's going to upgrade the degree of our approximations, saying rather than doing linear approximations from point to point to point to point, we're going to do parabolic approximations from point to point to point to point. So this is like saying we're going to put a bunch of different pieces of parabola to approximate the curve that we're attempting to find the area underneath. So if we want to improve our estimates of functions, we could use second order polynomials instead of first order polynomials to estimate the function of interest, right? We just did a linear approximation. We're now going to do a quadratic approximation. One very important note that makes Simpson's rule different than the rest is this. We've been doing a bunch of linear approximations, and what you know is lines require 2 points to make a line. And so we've had 2 endpoints on our rectangles. What you know is that quadratic functions require 3 points to make a parabola. So it seems like we're not doing things like averaging x0 and x1. It seems like we're going to need to use 3 x values to be able to define one of our approximating parabolas in each case right here. So one of the things that's special about Simpson's rule is we're going to be considering our x values in groups of 3 instead of in groups of 2 like we did with the midpoint rule, right? So this is like our upgrade specifically of the midpoint rule here, I think, is a good way to think about it. Or kind of a combination of the midpoint rule and the trapezoid rule in that they require 2 values each for those because those are linear approximations. Simpson's rule, quadratic approximation, is going to require us to think of 3 things together at once. So let's go ahead. This is going to be our fun math of the day here. We're going to derive our formula for Simpson's rule. The one limitation that we're going to see for Simpson's rule is this. We need to select points in adjacent groups of 3 to construct our approximating parabolas through 3 points, right? So this is kind of how I'm thinking about my grouping structures right here. So x0, x1, x2, x2, x3, x4, x4, x5, x6, stuff like that. Notice, importantly, that every group is going to end in an even subscript because we're always going to reuse, like 4 and 4 get reused, 2 and 2 get reused, but then that means that it's always got to end with an even. So one special limitation of Simpson's rule is you can't do an odd number of subdivisions. We have to have an even number of subdivisions so that we're always guaranteed to end on an even subscript, or else with our last grouping, we'd be trying to come up with a parabola with only 2 points, and that's not going to work out. So the one limitation for Simpson's rule, aside from the fact that it takes more effort, is going to be the fact that you have to have an even number for n. It's got to be the case. So let's come up with our formula for Simpson's rule on our own right here. So what we want to do is notice that all we've been doing this whole time is geometry because we can find the area of a rectangle with just geometry. We can find the area of a trapezoid with just geometry. The area underneath the parabola, we actually have to do an integral to find the area underneath one general Riemann object, right? And that's how we've been coming up with our formulas for these guys. These formulas are based on just geometry. But now our formula seems like it's going to have to be based on a sum of things that we get out of an integral right here, because I don't have a geometry formula that tells me the area under our one general Riemann object associated with the Simpson's rule approximation, right? So there will be an integral in this process that's right here, right? And this is our fun part. We finally get to do some math right here. So what I'm going to do, importantly, is draw a very useful picture for us right here. So I'm going to give us our general Riemann scenario right here. All right. So what I'm picturing for myself is I know I want to make like a general parabola. I'm going to put this parabola at the most convenient place that I can, where of the 3 points where there's a delta x distance from the middle to the left and from the middle to the right. I'm going to put the middle at 0 because I want this to be as conveniently located as possible, right? So my three x values of interest are going to be x is 0. X is, I'll call this guy h right here. H is like our delta x. I'm just not going to write a ton of delta x's out there. And x being negative h right there. So one h in each direction. You should think of h as like your h in your limit definition of the derivative. It is our delta x. That's exactly what it's defining in that case right there. So what we're doing is we're trying to approximate some parabola, the area underneath some, oh, that was a kind of bad parabola right there. Whatever. The point is that there's going to be these 3 points that are of interest to us. We want to know what are the x and y values associated with these points, and what is the area in this region of interest right here. So this is our region of interest. Right. So on both sides, that thing right there. So what I'm going to do is I'm going to label these guys a little bit more right here. I'm going to think of these as x1, or sorry, so I'm trying to keep my labels straight right here. There should be x0, this is going to be x1, and this is going to be x2. And therefore, I can think of this as being at the location negative h, y0. This is at 0, y1. And this is at h, y2. All right, so this is the kind of all the locations of interest for me associated with this parabola, where I'm trying to approximate the area underneath this shape. You should also notice something interesting about this, that it appears that our region of interest is 2 delta x's wide, no longer 1 delta x wide. It's because we require 3 points to make this thing, so there's going to be 2 subintervals contained underneath each of our approximating parabolas. All right? So how are we going to do this? Well, parabolas have general forms of y equals ax squared plus bx plus c. And so the area under one general Simpson's rule object how are we going to get it? Well, it looks like this is the integral from negative h to h of whatever our ax squared plus bx plus c is. Right. So let's go ahead and evaluate this definite integral here. And this will give us the area underneath one general Riemann object right here. That's just the thing we're going to want to add up a bunch of copies of. So I'm going to get 1/3 ax cubed plus 1/2 bx squared plus cx. I'm going to evaluate this guy from x equals negative h to x equals positive h. So I'm going to go ahead and get 1/3 h cubed plus 1/2 bh squared plus ch minus 1/3. This is going to be a negative 1/3 ah cubed, right? Because that was a negative h cubed. But notice, when I plug in negative h into x here, that negative gets squared, and so it's still, this term remains positive at a 1/2 bh squared. And then again, only one copy of negative h makes that a minus ch. And so you should notice that we're actually going to get cancellation of the b terms here. Right? I've got a positive 1/2 bh squared, and when I distribute this negative, I get a negative 1/2 bh squared. I can also see that I am getting 1/3 ah cubed, and another positive 1/3 ah cubed makes a 2/3 ah cubed. I can see positive CH plus another positive CH gives me plus 2CH. So it seems like, by the way, I can see that both these terms have an H in them, and I don't like fractions. And so I'm going to factor out an H over 3 from this guy, and that's going to leave me with 2AH squared plus 6C. Right? So it looks like that's my general area underneath one Riemann object, but this is in terms of A and C. What I would like this in terms of is in terms of like x0, x1, x2, y0, y1, y2. I want to use the points that I have, right? The whole reason we're using all of our x values and our y values. The whole point is I'm not going to like literally come up with the formula of the quadratic. I have the area of underneath the quadratic in general terms, in terms of a, b, c, or just the b canceled, so just a and c. But I want them in terms of the points of interest. So here's what I think we should do right here. I'm recognizing that we've got that, if f of x is our ax squared plus bx plus c, then it should be the case that we can do things like f of x0. That's the same thing for me as f of negative h, and therefore that's ah squared minus bh plus c. And that's the thing that we're calling y0, right? That's our output from x0. We can do the same thing here. F of x1, well, f of x1 should be f of 0 according to our picture. So that's actually just going to leave us with just c, right? Because the x went to 0, x went to 0, c is all that remains. That's what we're calling y1. And then we're also going to find f of x2 from our picture. That should be f of positive h. And that's going to give me ah squared plus bh plus c. And that's going to be our y2. So what we want to do is we want to build 2ah squared plus 6c from the expressions for y0, y1, and y2, right? And by the way, again, I feel like I just got to write this right here. H is our delta x in this case right here. So the point is here, I don't need to worry about the h over 3 because I've got delta x. It's not my thing of concern. My concern is getting rid of the a and the c. So that's the part that I'm trying to break down a little bit further here. And here's a really nice thing that I'm noticing. y0 plus y2, I'm looking for 2ah squared plus 6c. Well, I'm noticing that if I add y0 and y2, my bh's cancel. I don't want any b's. I get 2ah squareds, and I get 2c. Well, that's really close. We just need 4 more c. And notice that c is just our y1 right there. So it looks like y0 plus 4y1 plus y2 is going to be giving me exactly the 2ah squared plus 6c that we want. And so it looks like I've come up with a general formula here now. So it looks like our individual Riemann area h over 3 times y0 plus 4y1 plus y2. Looks like that's our total area underneath an individual one of those right there. What we're going to want to do, though, is we're going to add up a whole bunch of them. Should be equal to, or should be estimated by, this should be y0 plus 4y1 plus y2. Now we're going to, for our next one, we're going to start at our previous endpoint, y2, y3, but I just did that wrong right there. I know this should be 4y3 plus y4 plus h over 3. This is going to be y4 plus 4y5 plus y6. On and on and on out there. And the important thing that you can see from this is how many counts of each of our y values are we getting. It clearly looks like these h over 3's could get factored out from everything. And what am I seeing here? y0 plus 4y1. It looks like y2 is in there 2 times, right? Then there's 4y3's. Then there's 2 copies of y4. Then there's 4y5's. Then there's going to be 2 copies of y6. And we're going to keep on going here until we get out to our 2 copies of y sub n minus 2, plus our 4 copies of y sub n minus 1, and then we're going to get our final y sub n term right there. And that's what we're calling S sub n, our Simpson's rule approximation from a to b of f of x dx. Now, one thing that you can see if you take the time to go and do a whole mess of algebra is, I'm just going to say, it can be shown. Kind of my least favorite phrasing, but I know this video is long enough already. You can take a weighted average of the trapezoid rule and the midpoint rule to arrive at Simpson's rule by rearranging a bunch of these terms and playing with their coefficients right here. So notice that this is a 2n in the subscript. So if you're going to do something with like 10 subdivisions, then you would do 1/3 of the approximation you'd get from T5 plus 2/3 the approximation you'd get from M5 right there, stuff like that, right? So notice this 2n kind of trips people up occasionally right there. Simpson's rule of 10 subdivisions means that you could actually do trapezoid rule and the midpoint rule each with 5 subdivisions, and then take a weighted average, 1/3 of the trapezoid rule plus 2/3 of the midpoint rule. Turns out to give you the same thing as you'd get from Simpson's rule with 10 subdivisions. So let's go ahead and build our Simpson's rule in Python. Let's go ahead and check it against this formula that relates a couple of these things, and then we just got to talk about error bounds and call it a day. That'll be relatively brief here. So let's pop over to our Python stuff here, and let's build our Simpson's rule. This is a smidge tougher. We got to work out one little kind of slightly difficult piece that's associated with this here. The important thing here is being able to get the correct constant coefficient on each y term, right? So what we just came up with for Simpson's rule was that the integral from a to b of f of x dx is approximately that delta x, what we called h over 3. And our coefficients, notice we're going from y0 all the way to yn. Our coefficients are 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. That's going to be a bit awkward for us to build that in Python. We're going to want to kind of do that separate. It's not going to be too awkward to build, but like we need to think about that as a separate thing, you know. Further, we've seen that we should have this relationship of s sub 2n. Wow, that highlights terribly. S sub 2n equals 1/3 tn plus 2/3 mn. So we can use that to kind of check that our code works for Simpson's rule. And the one small difficulty is that we need to build an appropriate length list that looks like this thing. So what I want to do is I want to build a list that's just my coefficients, and then I'll take my list of coefficients and my list of y values and pairwise multiply them, then add that list up, and that'll get our sum of all of the y values with their appropriate corresponding coefficients out there. So this one's a little bit tougher thing right here. We got to use some kind of smart coding ideas right here. And so what I want to show you is that I'm going to get this guy I'm going to give us an n value here so that we can sort of check what we're going to want to do, right? So I'm going to pick an n value of just like 8 so we can see it. Notice I'm picking an even number. That matters right here. And what I want to do is I want to build what I'll call a coefficient list, coef list right there, right? I know it's going to be a list, but one thing I at least know about this list for sure is it starts with 1. But notice that even if n was like 2, we wouldn't necessarily go, I don't know, like, I want to make sure I'm building this list of the appropriate length of like getting these 4 2s, 4 2, 4 2, 4 2. So here's what I'm going to do. I'm going to say while the length of the coefficient list is less than n minus 2. So this is saying while we're still more than 2 away from the end, what I'm going to do is I'm going to stick on a 4 and a 2. And then a 4 and a 2, and then a 4 and a 2, and then a 4 and a 2. Once we get to 2 away from the end, that's when I'm done, and I'm just going to end with 4, 1, right? So while the length of the list is less than 2 away from the total length of the list, let's go ahead and do coefficient list. I want to add on to that. So plus equals will say keep the old parts of the list and add more lists to it. What do I want to add on? A 4 and a 2 as a little chunk of lists. Now exiting back out of that loop, I backspaced, so I'm done with the while loop part. It's just going to sit there and rerun that line of code over and over and over until the length of the coefficient list gets to be within 2 of the end. Then the last thing I need to do is just stick on a 4 and a 1. So now I'll do coefficient list plus equals a 4 and a 1. And let's see if we got it. Yeah, that feels really good to me, right? 1, 4, 2, 4, 2, 4, 2, 4, 1. That's exactly how this thing was set up to start and to end right there. And we could make this really long if we wanted. 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, all the way up to 1. And notice importantly, if we do 9 right here, which is illegal and we know that, 1, 4, 2, 4, 2, 4, 2, 4, 1, isn't that still actually... Okay, but these won't have y values to correspond with if we do it this way. So we still just want to stick to these evens right here to make that guy happen. What? But didn't it... Oh, I am seeing, right. So if n is 8 subdivisions, notice that 8 subdivisions leads us to 9 terms in the list right there. N subdivisions requires 9 fence posts to build 8 pieces of fence, right? Notice that by bumping n up to 9, we didn't get anything new in our list right here, right? We've got to bump it up to 10 before it will then give us 2 additional terms that are going to be in the list because we're adding these 2 at a time right there, right? So it looks like this is kind of built in the way that I've written this little piece of code, that this is guaranteeing to give us the 9 coefficients for the 9 y values associated with the 9 endpoints for 8 subdivisions. So that all looks good to me right there. So let's go ahead and write our Simpson's rule function right here. I guess I still want to mimic things from our old rule here, but this is going to be the most different of the previous ones. So let's define our simp rule right here. Simpson's rule. Still going to take in a function a, b, and n. We're still going to start by defining delta x, which we've been calling h. We're still going to want to get all of our x values here. And we're still going to want to get all of our y values. I don't think any of that stuff changes right there at all. But now I think the difference is that all these y values are going to need to get hit with our special coefficients that we're going to get from our coefficient list functions. So in the list all y, we want to get the corresponding coefficient. So all I'm going to do is just copy and paste this code in here. That's why I built that separately up there. Boom. And now I screwed up all my indentations, so I want to fix that. That should be in line with everything else. While should be, that should be indented because it's part of the while block. And then the last thing we do is we tack on the 4 and the 1 at the end right there. So now we've got our all y's. We've got our coefficient list. Now what we need to do is we need to build our actual y list that we're using by multiplying the ith term from all y times the ith term from the coefficient lists. Right? This is just coefficient times y, coefficient times y. Or sort of pictures as being like two lists that are sitting on top of each other, and we're multiplying coefficient times y value, coefficient times y value, coefficient times y value. Right? So I'm going to do the coefficient list, the ith thing in the coefficient list, times the ith thing in the y list. That's all. The ith coefficient times the ith y for I in range length all y. Right, so I want to do that for each one of the indices in the length of all y. So if all y was 10 things long, then I want to have there be indices of 0 to 9 right there to indicate all those guys. Finally, what we saw, one little special thing right here, is we saw that our formula said, so we've done this part. We've added up, we've come up with all of those appropriate numbers, the y value times its coefficient. I need to add them all up. And notice we're not multiplying by delta x, but by delta x over 3. Right? That's a little bit of a slight difference right here. So we're going to do dx over 3 times the sum of that y list, where the y list is not y's, but the appropriate coefficients being stuck onto those y's right there. And I think I'm good right here. But I want to do one other thing right now, because Simpson's rule has to have an even number of subdivisions. So I'm going to tack on a little bonus thing up top that's going to kick me out of this function if I try and give an odd n. Notice that, man, there's no restrictions on what I can do with that right here. So I want to say if n mod 2 is 1. So if you do division by 2 and there's a remainder of 1, then that means you're an odd number. And in this case, I want to just return, oops, can't spell return. And let's go ahead and return need an even n for Simpson's rule. And a nice thing in Python is that anytime you hit a return statement within a function that you've defined, it will just be done. It will just kick out, and it's saying we're not even going to see anything else. So if n is odd, then this will evaluate to true. It will run the code inside of it, and it will just say, I'm done evaluating this whole function. It'll skip all this code, and it'll just type out that sentence for me. If this is false, if n is in fact even, then it doesn't run this code, because this would be a false statement right here, and then it'll go on and do all the things we want it to do, and it'll return for us the area instead right there. So let's go ahead and see if we get some satisfying results right here. Let's do our Simpson's rule for the function f from 0 to 4. Let's do 10 subdivisions, and let's see right here. In fact, I want to do 9 subdivisions first to show you. Oh, I didn't run this block right here. Notice it said it's not defined. It's because I forgot to actually run it. So I'm going to shift enter this guy, and now it's got the number. I know that it's been run. If I give it 9, because 9 was in the n slot and n is odd, this statement was true. So it did run the code within the if statement, and it didn't do any math. It just said we need an even n for Simpson's rule. So now I'm going to change this to 10. And oh my goodness, Simpson's rule just straight up nailed it right there. It literally got the exact correct answer with only 10 subdivisions right there. That's pretty wild, but I don't think that's terribly surprising, considering we're approximating a cubic with with more polynomial pieces right there. So let's get a little bit crazier with this guy right here and let's see what happens if we go ahead and do our G guy right here. So if we're going so our G was from 0 to 2 that we were interested in. And again, I straight up don't know what this value was supposed to be, because I can't do the antiderivative for e to the x squared right there. So what I want to see is, are we going to get this relationship right here of that s sub 2n is 1/3 t sub n plus 2/3 m sub n? So let's go ahead and check this against our other things, and then see kind of how this thing kind of converges here. All right. So we can check this by saying that we've got it for 10. So now this should be 1/3 times our, what was it? I keep forgetting. 1/3 times the trapezoid rule with only 5 subdivisions. Plus 2/3 times the midpoint rule of G, 0, 2, and 5 subdivisions. And oh my gosh, we're getting the exact same thing with the exception of Python struggling a bare smidge with some, oh no, it just rounded this one more decimal than it rounded this one for some reason right there. That 1/6 got rounded to a 2 right there, but we're seeing that we are getting, and again, don't trust 16th decimal places ever with programming languages. Programming languages struggle with exact numbers because they have to use binary for things, and some numbers are just really, really hard to represent in binary. Again, we'll talk more about that out there in chapter 11, but it does seem like we see that getting satisfied right there. And I think another thing that we should do is we should do our little like for loop thing up here and see what kind of convergence we're getting on a value for that integral from 0 to 2 of e to the x squared. So let's see like how close do we really think that this is right here. Let's change this to Simpson's rule. Let's change this to g, and from 0 to 2. And it looks like this guy here, I mean, holy cow, this thing converged to like accuracy of like 6 decimal places at only 140 subintervals right there, as opposed to over here at 140 subintervals, we were still changing our 4th decimal place. So we have like 100 times the accuracy, or 100, 2 factors of 10 more precision at 140 subdivisions with Simpson's rule than we had with the trapezoid rule right here. So it seems like it's converging even faster than the previous ones, and that's because we're doing this second order approximation instead of a first order approximation. By the time we're getting out here, the difference between 190 and 200 subintervals, we don't see that till the 8th decimal place. We don't see a difference out there. So like, I'm pretty convinced that this thing has like converged for all meaningful purposes, for all practical purposes, I should say right here. And it never even started that far away. I mean, it looks like we were going to 16.4526. It started at 4902. Like we weren't far off even to start with only 10 subdivisions. Seemed like a really good estimate already. It didn't have far to go. So it seems like Simpson's rule is our most powerful rule. It seems like even if you couldn't do Simpson's rule, you can get the exact version of Simpson's rule with a weighted average of the trapezoid rules and the midpoint rules, which is also very practical since these are linear approximations that turn out just by linear combinations of our A's, B's, and C's that we used in that computation there. They just straight up give us Simpson's rule. So that's pretty dang cool right there. So Simpson's rule, by far the best approximation right here. And like if you go to your calculator and you ask it for areas under curves, which your calculator can do, I'm like 99% sure that TI calculators are just literally running this Simpson's rule code under the hood. This is like the code that's running in your calculator right here. So this is cool to like see where these values are actually coming from. Desmos, we know, also does these things, by the way. Here we could just do our integral from 0 to 2 of e to the x squared dx. Oops. And here's the 16.45267. 16.4526. Oh, that's interesting. It's got a smidge of difference. 452. Oh, 6277. That's exactly what we've got. 628 right there. So it looks like it's still got ever slightly more to go right here if we went further. Maybe let's just do this. Let's see where this really gets to. So now we're doing, notice I went on an additional factor of 10, but now it looks like this is going out. I mean, this matches Desmos to like every single decimal, right? And it was 77655, and we're ending with 77655. So we got it with Desmos, 77655. It looks like Desmos is even there. So if it's rounding correctly. So Desmos is maybe doing something like 1800 subdivisions for a Simpson's rule or something like that. And that's literally identical to Desmos right there. So I would not be terribly surprised at all if Desmos was also just running this code right there under the hood when it does your definite integrals for you right there. So we're getting the exact same answers right there. And that's not, and again, 1800 computations, it would take you a week. It takes a computer literally so little time that we can't even see how much time it took. Like less than a hundredth of a second right there for it to do that right there. It's a trivially simple computation for a computer to do right there, which is very, very cool, right? So now you know how these area computations are ever being performed. How are definite integrals ever evaluated by a computer? They're not doing calculus at all. They are using this formula of getting the appropriate coefficients and tacking them on to all of this, like just a grid of y values out there according to some subdivision, right? And that's all that's really happening right here. So this is, I really find great satisfaction in this because I always have felt like I'm really bothered when a calculator can just tell me some number and I'm like, but how does it know? Right here, we're getting it right here. This is literally the code that's being run in your TI calculator, that's being run at Desmos, and even Wolfram Alpha. There's not like techniques that are significantly better than this. So what you should also be thinking to yourself right now is, if we did better by going from linear to quadratic, couldn't we instead do like cubic and quartic approximations as well? And what we end up finding is that while those approximations do technically get a little bit better, the amount of additional computation that has to be done is outweighed by the smallness of increase in accuracy right there. So it's technically less computation to do more subintervals with a quadratic approximation than do less subintervals with like a cubic or a quartic out there. So there could be higher order analogs of Simpson's rule right here, but we're not getting better approximations with less computation in those cases right there, which is why Simpson's rule is typically where things sort of end at. We don't like go deeper than that. We can just do more subintervals and we basically get it. Right? Very cool. This is highly satisfying to me. That, and again, now we can come up with on our own approximations for definite integrals of even things we can't find antiderivatives of, essentially as accurate as we want right here, right? I can just make this number big. We can just do a million subintervals, and we basically get our answer right there, right? All right, I got to do that one time just for the sake of it, and then we'll do our error bounds, and then we'll call it a day here. So 100,000, 10,000, 100,000, a million. And ooh, man, it's actually that took a solid second for that guy to run right there. But again, I'm quite confident that this is now just going to be accurate to literally every decimal that you're seeing. That this is no longer every decimal here is correct according to the true value. If we could ever get a true value for this thing right here, I think that's matching to all like 16 decimal places or something like that. Really cool right there. All right. I hope that you appreciate that type of ability that we have as much as I do right there. Because even though this got a little complicated with our Python code right here, but man, I definitely expect that you guys can look at our left-hand rule and right-hand rule code and understand essentially every single thing that's happening here, even though you have no programming experience, because you know what the sort of algorithm is for doing the left-hand rule, and we're just mimicking it operation by operation within each of these functions right here. All we did today was build lists and did fancy addition, multiplication, stuff like that. Oh yeah, so Austin's saying I saw a video about Conrad Wolfram, which is the guy that started Wolfram Alpha, and talking about not teaching calculation, but instead teaching computer programming. Because again, like that was like always my dissatisfaction taking math classes, taking stats classes, and especially statistics. Is it's like every number you're looking it up in a table or getting it out of a calculator, and you never actually compute where any of those values come from. It's because all that stuff in statistics is like area underneath curves of like wild functions that you could never integrate. This is how we get all of those numbers right here. So, Austin, I am way down with what Conrad Wolfram says right there. I think that in the future, I think that all of our children are not going to take algebra as a course. I think they're going to take algorithms. It's the exact same Latin root word, but the whole point here is we're describing a process. I think it's a bad thing to think about this as a calculation. This is a process that we just described, and we're letting the programming handle it for us. So like my fantasy of math education is that we will literally basically stop teaching algebra, or maybe you get 1 year of algebra in like 7th grade, and then from then on we're just going to be teaching computer programming, because this actually gives us the tool that's actually being used. Because at the end of the day, most people aren't really doing integrals by hand, right? They're going to hit them with Simpson's rule every single time. In fact, if you go to other Python packages where the integration is done for you, there is no function called definite integral. There is scipy.integrate.simpson. It's straight up just, the function is just called Simpson's rule and not integral, because it's just, that's how it's done. And so, yeah, I'm a big time into this. The other thing that's cool about this is that if you guys have any programming experience, then you'll recognize that this like cell-based writing of code is very different from most other code writing where you write like a long script and then just run all of the code that you've written all at once. Whereas here today, we were running little bits of code at a time. This whole Jupyter notebook setup thing was inspired by Mathematica because Mathematica notebooks does exactly this, where you write a cell and run it, but then you can write some English, you can write some LaTeX, and you can switch back and forth between code and English, code and English. That's another thing that the Wolfram people collectively are very much fighting for in academia, is to say, it's ridiculous that anybody ever publishes a research paper as a PDF ever for the rest of history. If you're ever doing science, then I want to literally be able to play around with your data in a notebook. And 100% of all research that's ever done in the future should be digital notebooks to where I can go in and see what function did they use to estimate that value. How did they produce this graph right there? Are those good axes for this graph? When I get static PDFs of things and I can't really see what happened under the hood, I'm not as convinced that everything's legit. If your science is actually good, then I should be able to play around with exactly the math that was happening under the hood. I should be able to see it directly, manually alter it, try things on my own. And so Wolfram's big thing is we shouldn't be doing, like, if you research as a PDF should be considered not acceptable anymore in the future, and it should only be notebooks like this where we have code, math is being done, functions from other libraries are being used, and the exposition, the writing, should be happening interwoven with the calculation right there. Yeah, a room with Google Eyes, the compile button still gives you anxiety. None of that here in Python. This is an interpreted language rather than a compiled language. That's nice. So any of you that are planning on being scientists in the future, get on board with it. This is how the future of science is going to happen, is by you learning some basic programming and being able to prove to people that your stuff was legit, not by printing out a page, but by having a digital document that anybody can see the inner workings of, so that way people can actually trust that what you did was actually legitimate. This is the future of how science will be done. And again, Jupyter was this is officially a Wolfram Alpha idea that was stolen by Jupyter Notebooks, and they're open about it. They're like, we love that cell-based style. That's why we built this thing this way. So this is an intention to mimic Mathematica right here and the structure of how this code is written. So all cool stuff. Don't be afraid of learning to program. The year is 2021. If you think that you're going to do anything related to math or science at all and avoid learning programming, you are lying to yourself. Python is the friendliest programming language to learn that's ever been made, aside from literal programming languages that are designed exclusively to teach children to program. This is the most practical language that is the easiest to learn. I think you should do it if you think that you are anything of a mathematician or a scientist or an engineer or anything like that. This is how your work is going to get done right here. So let's go wrap up our day. I know this is a long video, but we got to wrap up our final topic right here. And that is that we got to take a gander at error bounds right here. We're just going to do a couple computations and we're going to be done right here. What you're all going to go do is every one of you is going to go to grad school, and every one of you is going to not do the one wrong thing that I did. Well, okay, I did a couple wrong things in grad school, but one of the things that I did wrong, yeah, and so Austin, you're saying it right there in chat. ArcGIS, that works in Python. Like, Python supports so many things that touch every single branch of science. I don't care what branch of science you're going into. Python has specialty libraries that help you tackle every single thing like that. It's so broadly spread. It's really excellent. You can really learn one language and be capable of doing a massive amount of different stuff. It's really powerful. So one of the things that I regret from grad school is I, just due to a stupid scheduling conflict, didn't end up taking a class in numerical analysis. Numerical analysis is a class that's essentially going to be an entire class like today's day right here. How are all of these things approximated? How do we approximate? When you ask your calculator for where is the root of a function, how does it give you an approximation accurate to 8 decimal places? That you're going to learn that in numerical analysis. How do we do Simpson's rule? How do we approximate solutions to differential equations? I'm literally teaching that this week right now in Math50B. All those good sorts of things. So in numerical analysis, when you go to take that, when every one of you go to grad school and take numerical analysis, you're going to do things like derive where the formulas come from for the error bounds. It's a little bit complicated as to how do we come up with these error bound formulas, so it's not really within the scope of this class. But the book does just straight up give us the following theorems associated with bounding the error on our approximation. So this is saying things like, if I were to estimate this integral from a to the, of the function f of x over the interval from a to b with n subdivisions, can you tell me the most off I could possibly be by? That's what we're saying by bounding our error. I want to know, I want to be able to say, listen, I am positive that this approximation is accurate to within zero point 0.7. I want to be able to come up with statements like that. Other things, I want to be able to invert that statement then to say things like, I need an approximation that I know is accurate to within 0.0001. How many subintervals do I need to use to get that desired precision that we're looking for right there? So those are two error-bound pieces of information that we want to be able to discuss here. So error bounds for the midpoint rule, trapezoid rule, Simpson's rule. The book straight up just tells us these, so I've just copied them in right here. And I want you to don't look too carefully at this. I want you to see some broad things right here. One, absolute value of the error, because these are telling us error is either an above amount or a below amount, right? You could have underestimates or overestimates. We're not trying to drag in the positive negative associated with our errors. They're all within absolute values. I'm subscripting them with M, T, and S for midpoint trapezoid Simpson's rule. And this is a bound on the error. So this is saying our error is guaranteed to be smaller than some number that we can compute. Unfortunately, they all involve this k term, where k is a bound on the magnitude of a derivative. And notice that the midpoint and trapezoid rules involve second derivatives. Simpson's rule kind of unfortunately involves the fourth derivative of your function to help you determine k. But this is saying find the absolute biggest value that your fourth derivative ever gets to over your a to b interval. That is an acceptable value for k that you can use right there. The remaining parts of this term are just, b minus a, it looks like it's cubed, or to the fifth power for Simpson's rule. We've got some weird coefficients down here. Notice we identified, by the way, that the midpoint, or that the trapezoid rule seemed to be having half of that error as the midpoint rule. You can see that difference of 1/2 exactly in these two expressions. They're almost identical. They're off by a factor of exactly 1/2. We saw that 1/2 come out in our computations about 30 minutes ago there, right? And it involves the number of subdivisions. So all three of these have an n in there as well. So while we're not doing any of the derivations for these because they're kind of complicated, you should see that they all are of the exact same structure. It looks like they're going to be different because of the fact that the first two are linear approximations and this is a quadratic approximation. So that's changing some of the powers that we see and the number of derivatives, because this k is based on a fourth derivative, whereas this k is based on second derivatives for midpoint and trapezoid. They all have the same exact structure right here. So definitely don't memorize these. You just got to be able to use these in a practical sense. So let's go ahead and do two problems with this and call it a day. In all three cases, the parameters of interest are E, N, K, B, A. You'll always know A and B. If we know any two of the remaining three terms, E, N, and K, we can solve for the third. Since knowing K is required for the hypothesis of the theorem, that means that there's only two possible scenarios. If we can identify K by doing some math, and identify the desired error, that's just what your boss is going to tell you your maximum allowable error is, then we can solve for n, the number of subdivisions you can get away with doing to still get within your desired error. So this is like an optimization thing. Maybe your computer is going to have to do Simpson's rule 1 billion times in a day. You don't want to be doing 2,000 subintervals if only 100 will do, because it's going to take 20 times as long for your computer to do that process, right? So this is saying how few subdivisions could we get away with and still get an acceptable amount of error. We could also flip that around and say, if we can identify K and we know how many subdivisions we're going to use, we can determine the maximum amount of error we might end up with if we use that many subdivisions, right? So there's sort of the know N and get E, or know the needed E and get the allowable N, right? Those are the two things we'll do right here. So we'll go ahead and do our e to the x squared as we have identified. Suppose we want to estimate the value of the integral from 0 to 2 of e to the x squared using Simpson's rule. Remember, we straight up can't do this integral. The best we can do is approximate it with Simpson's rule. We want to know how good our approximation is going to do. Right? So our two questions are, if we use 10 subdivisions, not very many, what's the maximum possible error we might see? On the other hand, if your boss comes to you and says, hey man, I need you to approximate this efficiently, you need to get an error of no more than 0.00001, how few subdivisions can we get away with doing? We don't want to do more work than necessary, right? In both of these cases, we need to find k. And for Simpson's rule, unfortunately, k is bounded by the largest possible value of f to the fourth, or sorry, the fourth derivative of f. Okay, so I'm going to have to take a bunch of derivatives right here, but I can handle this. I haven't done calculus really yet today, so I'm gonna do some calculus here. I'm going to take some derivatives. So let's go ahead and hit this bad boy here. So we've got that f of x is our e to the x squared. F prime of x, we got to do some chain rule here. Outside function, e to the x squared times the derivative of the inside, that's going to be a 2x. I might write that as 2x e to the x squared. So now when I take my next derivative, I see that I'm going to get a product rule right here. So product rule, we've got our first chunk and our second chunk right there. Product rule says take the derivative of the first and leave the other chunk alone, plus leave the first chunk alone and take the derivative of the second. That's going to give me another 2x e to the x squared. Right? And I might simplify this lightly as 2e to the x squared plus 4x squared e to the x squared. Now for my third derivative, I'm going to just take the derivative of the first piece, so that's going to give me 2 copies of the derivative of e to the x squared. We've already found the derivative of e to the x squared is 2x e to the x squared. I'm multiplying that by 2, so I'm going to get 4x e to the x squared. That's the derivative of the first term. The derivative of the second term, I'm again going to product rule this guy. 4x squared and e to the x squared are my 2 parts. I'm going to take the derivative of the first part, and I'm going to leave the second part alone. Plus, I'm going to leave the first part alone. I'm going to take the derivative of the second part. I'm going to simplify this for myself, clean it up so I can take one more derivative easily here. So 4x e to the x squared survives. Here I've got 8x e to the x squared. And here I've got 8x cubed e to the x squared. So that is going to give me a total of 12x e to the x squared plus 8x cubed e to the x squared. So unfortunately, we've got to do the product rule for both of these groupings here, but this is our last derivative that we have to do. So let's do one more layer right here, and we'll have f to the fourth. So derivative of 12x is 12. Leave the other part alone. Plus the 12x gets left alone, and we take the derivative of the other part. That's our first derivative. Our second derivative is take the derivative of the first part. That's going to give us 24x squared. Leave the other part alone. And then we leave the 8x cubed alone. And we take the derivative of e to the x squared. 2x e to the x squared. Let's just simplify this guy, and we have got an expression for f to the fourth. So 12 e to the x squared plus 24x squared e to the x squared plus 24x squared e to the x squared from the other group, plus 16x to the fourth e to the x squared. And it looks like I can simplify this as everything has e to the x squared. Everything's, I'm just going to leave the coefficients alone, I guess. I'm just going to leave that. So we're getting to 12 here. This is 24 plus 24 gives me 48x squared. And then a 16x to the fourth. So there's my f to the fourth of x. Now, here's the deal. What we need to know is what is this what's the upper bound of this? We want want k. I got ahead of myself there. On our interval a to b. Well, if we go pop over super quick to Desmos, then what we'll be able to see here is that this function, let's go take a look over here. We've got e to the x squared times 12 plus 48x squared. And man, is this not like the steepest function like on Earth right here? 12 plus 48x squared. These function values just get massive instantly. 16x to the fourth. And holy cow. So the important thing is this. This function, oh my God, this thing just gets so, I mean, obviously just plugging in 2 gives us huge numbers. But the important thing is this. We can see that this function is increasing and concave up. Therefore, it's going to reach its maximum value at its rightmost endpoint. That's kind of a takeaway that I can see right here. So I'm going to use that piece of information to know that we're really just looking to evaluate this at 2 to get our good value of k. So basically that says to me k needs to be the upper bound on the fourth derivative of f. Since the fourth derivative of f is strictly increasing, I'm just going to compute the fourth derivative at its upper bound of 2, and that should be the largest y value that we ever get out from the fourth derivative. That's a good upper bound value that we can use for that k value right there. So f, the fourth derivative of f at 2 is e to the fourth times 12 plus 48 times 4 plus 16 times 16. And that is going to be giving me, let me see, I'm just going to get my e to the fourth times 12 plus, that's 192 plus 256. And that's going to be e to the fourth times, that'll add up to be 460 right there. So this is what I'm going to use as my k value right there. All right. So using that, I can now go ahead and find my 2 values, and then we're finally done here. I know this guy went long here. So if we use 10 subdivisions, what's the maximum possible error? Well, I can just say that our error here, ES, our error on the Simpsons rule with 10 subdivisions, it's going to be e to the fourth times 460, that's k, times b minus a is 2 minus 0 to the fifth, divided by 180 times 10 to the fourth. And if we go ahead and we take that guy to a calculator here, what we're going to find is we're going to get that our error from the Simpsons rule with 10 subdivisions of this function is guaranteed to be less than or equal to 0.4465. So the point here is that we can use this bounding rule. If we can compute k, then we can guarantee that we know exactly the maximum amount of error we could possibly have. And it certainly could be less error than this. This is an upper bound on the amount of error. And again, it's very particular to this problem. That's particular to the f function that we're using. It's particular to the a to b bounds. It's particular to the number of subdivisions. It's particular to us using Simpson's rule. But we've now computed a guaranteed upper bound on the error. Now, our slightly more interesting computation here is saying if we want an error of no more than 0.0001, how many subdivisions can we get away with using? So in this case, we've been given e sub s. We want to know n. So we can say 0.00001 is less than or equal to, using that gross k value here of e to the fourth times 460, again, times 2 minus 0 to the fifth, all divided by 180 n to the fourth. Well, I'm just going to throw all my values over here onto the other side of this thing, right? I'm going to say 0.00001 times 180, all divided by e to the fourth times 460 times 2 to the fifth. And that should be essentially, I'm going to say that's going to be equal to the number of n values in quotes right there. And that should be 1 over n to the fourth, right? So that means I can flip this fraction and take a fourth root. I'll say n is approximately equal to e to the fourth, 460, 2 to the fifth, over 0.00001 times 180. And we're taking so I flipped it because it's 1 over n to the fourth. I flipped my fraction and I took a 1/4 power to get n. And if you go to your calculator with this guy, you'll get 145.36. Now, got to be careful with this one here. Rounding rules might suggest to you that our number of subdivisions should be 145, but super importantly right here, you should notice if we use an n value that's less than 145.36, then that is not enough subdivisions for us to get the desired error. So we always, in this case right here, will always round up. Even if you got a 1 point or 145.01, that means that you need 146 subdivisions because you got to get a whole number. And if you do fewer than the decimal number that we get out for n, then you don't have enough subdivisions to get the desired, to be guaranteed the desired error. So we always will round this up. That says to me an n value of 146 is sufficient to be guaranteed to be getting accuracy to within 5 decimal places right there, or to be within off by 1 at the 5th decimal place right there. Oh, and good call right there. Also must be, yeah, good call. So even if that was a 144, yeah, I'm going to actually write this right now. The comment in chat that I'm seeing is it also must be an even number for Simpson's rule. So I'm going to say here as my final comment of the day. Oh, am I going to say it? Or is, all right, here we go. Okay. So that wraps it up for today. So again, uh, I never learned to program basically until on my own after grad school. I taught myself 100% of all the coding that I need to know. All the programming that you saw me do today, I whipped up this morning in like 40 minutes before this lecture right here because I have taught myself sufficiently that I am like really, really, really confident in using my math and programming skills together. Um, I self-taught myself all this stuff. You guys are still in college, so you have the advantage over me, which is that you can actually learn this with other people in courses that are designed to help you learn this instead of just flailing around like I did all the time. So you should really do that. I'm going to say it again as my closing comment today. If you think that you are going to be literally any form of scientists, the year is 2021. There's no science that's happening on paper. 100% of it is going to have at least some relationship to writing code. So delaying it is just making things harder for yourself later. Python is the friendliest language to learn and handles, I know this is an insane statement for me to make, but I'm going to say it. Literally everything you're ever going to want to do scientifically. The only reason anybody needs other languages other than Python is if you need to write code that runs really, 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 really fast. Python is not the fastest language out there. So things like when you do a Google search and it returns to you like 80 billion results in less than a second, Python could never do anything that quickly, but I don't need to do things quickly in science because to me, I can't tell the difference between 0.01 seconds and zero point 0.1 seconds for runtime for any code, so I don't care. So in some data analysis things where but then that's really just more Google stuff. If you're trying to analyze a data set with 80 million rows, yeah, you might step out of Python to do some of that stuff right there, but like this is a language that you should be learning. It's really friendly. It handles all of your scientific cases, all of your mathematical cases. and it's friendly. It's not like learning to program in 1980s with kind of unfriendly languages out of a textbook. It's not like that anymore. So if I can teach myself how to do this completely alone, then you can definitely learn it with support of your classmates and your instructors and stuff like that. And me. So do this. If you want any amount of help at all, getting into some Python things, it's sort of my favorite thing to do and to talk about. And so I would really appreciate getting that kind of contact with you guys there as well. So look to download the Anaconda installation of Python. Don't do Python alone. It's going to require you to then do like several parts separate. Anaconda installation wraps it all together in one. So do that. And so I'm going to wrap this up. I promise this will be my longest video of the year, but I had to go a little bit long to get that really good code content in there. So I'll post that code in Canvas as well, and I will see you guys for our other topic this week is improper integrals. That's basically going to say what happens when we have bounds on integrals that go to infinity. What happens when the y values within our integrands go off to infinity? So section 7.8 is saying already this class is about infinity enough. But what happens when we like explicitly put the number infinity in for x or for y? How do we handle that? And that's what we're going to talk about in 7.8. It's not going to blow your mind too badly. I think our concepts in 7.8 are relatively easy. And I think that's our last section in chapter 7. And then we'll get into chapter 8 stuff. We get a bunch of super cool applications right away in chapter 8. Surface area, arc length, probability topics, bunch of really cool stuff coming up in chapter 8 here as well. So I will see you guys for our 7.8 video. Have a good one, everybody. Thanks for being there in chat, guys.